Welcome to another episode discussing the research projects developed by the Applied Computing Research Group, GCA. Today we're diving into some really fascinating work by a dedicated team of researchers. That's Matthias D. Kuhn, Marcelo P. Checkin, Marcos V. Hart, Gerson Battisti, Fabricia Ruz France, Rafael Z. France, and Sindosa Wiki. So I want you to just imagine for a second a single microscopic fungal spore. It's just drifting on the wind, right? And it finally lands on this damp soybean leaf in rural Brazil.
Yeah, which historically is a nightmare scenario for a farmer.
Exactly. I mean, in the past, that invisible spore landing in those perfect conditions basically meant a ruined harvest. But today we're looking at a project designed to catch that spore's ideal environment before the farmer even wakes up.
Right, because we are talking about taking cutting-edge Internet of Things technology, so complex software engineering, radio wave propagation, database management, all of that, and completely pulling it out of the sterile, conceptual laboratory. The team literally dropped a fully operational infrastructure straight into the mud, the wind, and the just relentless rain of real-world farming.
Yeah, into the elements. So the mission for our deep dive today is to really figure out what happens when you do that. We want to understand exactly how this invisible digital nervous system works. Because, a nervous system doesn't just sit there feeling the temperature, right? It transmits, it processes, and then it triggers a reaction to save the organism.
And to really grasp how they built this, we have to look at where this nervous system has actually been implanted.
Right. The location is key here. We are heading to the northwestern region of the state of Rio Grande do Sul in Brazil, specifically a municipality called Santa Rosa.
Which is really just the perfect crucible for this kind of experiment. I mean, Santa Rosa is widely recognized as the national birthplace of soybean production in Brazil. It's an absolute powerhouse of agribusiness.
So the economic stakes here are just incredibly high for the people living there.
Oh, absolutely. And the work we are analyzing today is actually the fusion of two major institutional projects. First, you've got the Smart Life Lab, which is dedicated entirely to prototyping the physical IoT solutions. The hardware, the antennas, the actual connectivity.
Gotcha.
And then on the other side, you have the Living Lab Agro Noroeste Missões. And their entire purpose is to take the raw data generated by that hardware and translate it into actual actionable intelligence for agriculture.
Okay, let's unpack this setup, because reading through how they integrated these two labs, it brought a really specific analogy to mind.
Oh, yeah. What's that?
Well, studying software engineering and IoT purely in a university lab setting, it feels a lot like buying this pristine, state-of-the-art, four-wheel drive off-road vehicle, right? But you only ever drive it on a smooth, paved indoor test track. Sure, the engine purrs, the specs look phenomenal on paper, but you don't actually know if the vehicle works until you take it out into the wild.
Right, until you hit a real pothole.
Exactly. You have to drive it through a flooded, muddy ditch to see if the suspension actually holds up under stress.
That distinction is basically the entire foundation of this paper. I mean, if you survey the existing academic literature on LoRaWAN technology, which is this specific radio network they're using in these agricultural settings, you will find a mountain of studies, just a ton of them.
But they're mostly theoretical, right?
Yeah, a staggering number of them are purely conceptual. They're just mathematical proposals, or they're run in these highly controlled, simulated environments where a computer just pretends to be a farm.
Right, the indoor test track.
Precisely. What this paper details is a real deployed operational environment. Because when you deploy delicate electronic hardware and, complex software into the dynamic, chaotic real world, you are immediately hit with variables that no algorithm can perfectly simulate.
Oh, I bet. Like what kind of variables?
Well, say a bird decides to nest on your wind sensor, stopping it from spinning. Or a massive electrical storm just knocks out power to your central gateway. Or maybe the temperature out in the fields drops significantly faster than the simulation predicted, which causes condensation to form inside the supposedly sealed data box, and then it just shorts out the motherboard.
Wow, yeah, you can't code for a bird making a nest on your anemometer.
Exactly. Having a live testing ground in Santa Rosa is absolutely crucial for evaluating these solutions. Real-world agribusiness doesn't happen in a vacuum, It happens in the dirt.
So let's visualize what they actually built out there in the dirt. Because if you were to drive out to Santa Rosa right now, navigating through both the dense urban center and out into rural districts like Timbaúva and Cruzeiro, you'd see this infrastructure literally bolted to the earth.
Yeah, it's a very physical presence.
Out in the elements, They have erected these really sturdy metal poles against the sky. Clamped to the pole is this heavy-duty black enclosure box protecting all the delicate transmission hardware.
And power is always an issue, so right above that, you have a small solar panel angled to catch the sun, basically keeping the system powered indefinitely.
Right. And at the very top, you've got an anemometer, those little cuffs spinning to capture wind speed, right alongside a rain gauge.
And those stations are basically acting as the sensory organs of that digital nervous system we talked about earlier. They are continuously pulling in a wealth of physical variables. We're talking temperature, relative humidity, precipitation, wind speed, luminosity, and even UV radiation.
So they're really capturing the exact physical reality of that specific microclimate.
Yes, but capturing the physical reality is really only step one of the whole process.
And here is where I need you to kind of break down the nuts and bolts for us, because this is happening out in the middle of nowhere. A gust of wind hits that anemometer, the temperature suddenly drops. How on earth does that physical event in a remote soybean field actually become a data point on a researcher's screen?
Right, so it requires this highly orchestrated six-step technological pipeline. When that drop in temperature is recorded by the sensor, it obviously needs to leave the physical station. This is step one, where LoRaWAN comes in. The station encodes that temperature reading into a tiny radio wave and broadcasts it outward, just invisibly over the fields.
I have to stop you there, actually, because it is 2026. Every farmer out there has a smartphone in their pocket. Why use LoRaWAN at all? Why not just hook these sensors up to regular Wi-Fi or the cellular networks that already exist?
That is a great question, and it really comes down to power and physics.
Yeah.
Think of a standard Wi-Fi router like a high-definition digital projector. It can send massive, beautiful amounts of data like streaming 4K video or downloading huge files, but it takes a ton of power to run.
Yeah, and the signal barely makes it out of your living room.
Exactly. Now, a cellular network has much better range, but it still drains batteries incredibly fast. If you put a 5G modem in a weather station out in the middle of a massive soybean field, you would have to send a technician out every few days just to swap the batteries.
And I'm guessing there are no extension cords running 3 miles down a muddy dirt road.
Definitely not. So LoRaWAN, which stands for Long Range Wide Area Network, is completely different. Instead of a high-definition projector, LoRaWAN is more like a lighthouse blinking Morse code. It is sending incredibly basic, tiny packets of information, just a few bytes of data that essentially say, temperature is 22 degrees.
Oh, okay, so it's super lightweight.
Exactly. Because it's only blinking Morse code, it takes almost zero energy to transmit. That little solar panel provides more than enough juice. And because of the specific radio frequency it uses, that low-power whisper can cut through miles of air and vegetation to reach a receiver. It's really the only viable bridge for this kind of extreme isolation.
Okay, that makes sense. So the station blinks its Morse code radio wave across the fields. Where does it actually go?
That brings us to step two. It hits one of the LoRaWAN gateways. These are essentially massive omnidirectional antennas placed strategically all around the municipality to cast this huge invisible net over the farms. The gateway catches that radio wave and forwards it to step three, which is a network server called ChirpStack.
ChirpStack. What exactly is ChirpStack doing? Is it just like a digital storage filter?
Not quite. Think of ChirpStack more as the bouncer at the door of the network. It receives this raw radio frequency, checks the cryptographic security keys to make sure the data is actually coming from one of their trusted sensors and not just some random interference. Then it demodulates the radio signal, strips away the radio wrapper, and leaves you with the raw digital payload.
But that payload isn't readable yet, right? Which brings us to step 4, I assume.
Exactly right. ChirpStack hands that payload over to a tool called Node RED. Now, the payload at this point is usually just a string of hexadecimal characters, basically machine language. Node RED-J acts as the digital translator. It's a processing engine that parses that raw hexadecimal string and maps it logically. It says, these specific bytes represent 45% humidity, and these bytes over here represent wind speed.
So it turns machine code into human-readable data flows.
Exactly, which flows perfectly into step 5. Node RED takes that clean, translated data and injects it straight into a PostgreSQL database.
Which is the permanent storage, right?
Yes, PostgreSQL is the permanent relational ledger. It organizes everything into vast, easily searchable tables, permanently storing the data.
And finally, step 6. That database feeds directly into the operational dashboards, the charts, the graphs, the real-time maps, so that physical drop of rain out in the field has successfully become a digital pixel on a screen. But, now that we have this incredibly elegant pipeline permanently storing all this hyperlocal data, we really have to ask what they are actually doing with it.
And this is where the Living Lab Agronoroas Missonzers project really proves its value. A standout example from the paper is the 2024 master's thesis by Matthias Kuhn, who is one of the authors. He basically utilized this continuous stream of precise temperature and humidity data to compute what they call favorability indices for Asian soybean rust.
And Asian soybean rust, just for context, is not a minor inconvenience. It is a devastating biological threat. It's caused by a fungus called Phacophthora petrilevi. When those spores land on a plant, they multiply rapidly, causing these massive lesions on the leaves. The leaves turn yellow, they drop off prematurely, and without leaves, the plant obviously can't photosynthesize. The pods don't fill. If it isn't caught immediately, it can absolutely decimate a crop's yield in just a matter of days.
Right, and the key here is that the fungus thrives under highly specific microclimate conditions. It requires a really precise window of temperature combined with an extended duration of leaf wetness.
So with this system, the farmer doesn't have to walk hundreds of acres of fields blindly, just hoping to spot a single yellow leaf before it spreads to the next acre. The software system is constantly analyzing the exact conditions of the air directly above the crops. It's generating a real-time phytosanitary risk analysis. But wait, I have to push back a little here. Farmers already have weather apps on their smartphones. Why go through the monumental effort of building a massive custom hardware network just to tell them it's humid?
What's fascinating here is the massive difference in resolution compared to what most people are used to. When you look at commercial weather apps, you are largely looking at generalized radar interpolation. A high-end weather station at a municipal airport 20 miles away reports that it's 75 degrees and slightly humid. The algorithm just guesses that it's probably also 75 degrees on your farm. But agricultural microclimates vary wildly.
Right, like a valley on a farmer's land might hold morning dew for, 3 hours longer than the elevated hill right next to it.
Exactly. And 3 hours of leaf moisture is exactly the difference between the rust fungus dying off in the morning sun or taking hold and destroying the crop. A generalized airport radar cannot see the dew in that specific valley. But the LoRaWAN sensor, physically standing in that valley, definitely can.
That makes total sense.
But it goes way beyond just checking today's humidity. By routing all of this data into their own PostgreSQL database, the researchers and the farmers are creating a continuous historical time series dataset. They literally own this raw material. They aren't renting fragmented data from a third-party corporate weather service.
They're building a permanent archive of their own land's behavior.
Which is the fundamental requirement for future software engineering. If a researcher in, say, 2030 wants to train a sophisticated machine learning model to predict a completely different agricultural anomaly, they cannot do it without a rich, hyperlocal historical dataset to train the algorithm on. This deployed infrastructure is stockpiling the exact data needed for innovations that haven't even been invented yet.
Wow. And that's just the agricultural side.
Yeah.
But the paper doesn't stop at the edge of the fields, does it? It brings this exact same infrastructure into the concrete and asphalt of the city itself. They highlight a 2025 study by Valente and colleagues that shifts the focus to a smart city initiative right within Santa Rosa.
Yes, and moving from a flat soybean field into a dense urban center introduces an absolute nightmare of physics. You are suddenly dealing with tall buildings that absorb radio signals, hills that block line of sight, and intense electromagnetic interference from city infrastructure.
Which means you can't just stick an antenna on a pole and hope for the best.
Precisely. To solve this, Valente and the team used a fascinating approach called search-based software engineering. Instead of manually guessing the best spots to install these LoRaWAN gateways in the city, they turned the problem into an algorithmic search space.
So how does that actually work in practice? Are they just running simulations?
Kind of. They feed a topographical and architectural map of the city into the algorithm. The software then generates thousands of potential gateway placements virtually. It mathematically scores these configurations based on how well the signal propagates, factoring in the signal decay caused by concrete and the blind spots created by hills.
Oh, wow.
Yeah, it essentially crossbreeds the most successful mathematical configurations over and over again, almost like digital evolution, until it finds the absolute mathematical optimum for both coverage and cost. And they do all of this before they drill a single hole in a real building.
So they are using advanced software to optimize the physical architecture of the hardware network itself.
Ah,
That is brilliant, and it perfectly sets up the massive evolution this project is currently undergoing.
hmm.
Because, they have the basic sensors, they have the optimal city gateways, but they are aggressively scaling up the computational power of the living lab agro-norest mesons.
Oh, absolutely. The foundation is set, and now they're just layering immense processing power right on top. The paper outlines the integration of NVIDIA GPUs, specifically dedicated to running complex artificial intelligence and machine learning experiments directly on this incoming data stream.
And the data stream itself is getting a massive upgrade, too. They're bringing in aerial drones equipped with LiDAR sensors. And for you listening, these aren't just taking photographs. LiDAR shoots millions of laser pulses down at the ground, measuring the exact time it takes for the light to bounce back.
Yeah, it creates a high-resolution, three-dimensional point cloud. So they're capturing the precise topography of the land, the varying height and density of the crop canopy, and mapping soil variations literally down to the centimeter.
It really makes me think of it like a massive skill tree in a role-playing video game. Like you start the game at level 1, and you unlock your basic sensory input, so temperature and wind data over LoRaWAN. But as the system gains experience, you spend points to unlock entirely new sensory branches. Suddenly, you unlock the LiDAR drone mapping ability, giving the system 3D vision. Then you unlock NVIDIA GPUs, giving the system a heavy-duty frontal lobe for AI modeling. The system is just acquiring new senses and a bigger brain simultaneously.
That's a great way to put it. But as any software engineer knows, adding complexity introduces fragility. This is why the research team rigorously evaluates the entire ecosystem using strict key performance indicators, or KPIs. They aren't just assuming the tech works because it's expensive or flashy.
Right, they have to prove it survives the mud.
Exactly. They measure network availability. So, is the ChirpStack server actually online and catching data when a severe storm hits? They monitor the data delivery rate. Are those tiny LoRaWAN packets getting lost in urban interference, or is the PostgreSQL database receiving everything sent by the nodes? They relentlessly test the measurement reliability of the physical sensors against actual calibration standards. Because this is the only way to prove a software engineering solution is viable in a chaotic physical environment.
The meticulousness of it is staggering, honestly. And for you listening, whether you are deeply embedded in ag tech or have literally never stepped foot on a farm, the implications of this infrastructure affect you. The resilience of our global food supply chain really hinges on our ability to bridge this massive gap between the unpredictable violence of natural weather environments and the precise logic of advanced software engineering. It's about systematically replacing agricultural guesswork with hard, hyperlocal, mathematically proven data.
Because agricultural margins are continually shrinking, right?
Yeah.
While environmental variables are just growing more extreme and much harder to predict, a digital nervous system that can preemptively identify a localized fungal outbreak before it spreads, that is literally the difference between a secure harvest and a catastrophic regional loss.
It is a profound shift in how we interact with the earth. And it leaves me with a thought that I have been mulling over since we started digging into this research. We are watching this infrastructure rapidly expand. The LoRaWAN gateways are optimized. LiDAR drones are preparing to map every inch of the canopy in 3D, and these massive data streams are flowing into NVIDIA GPUs for AI analysis.
Right.
But historically, farming has been deeply rooted in human intuition. The generational knowledge of a farmer who looks at the sky, feels the humidity in the dirt, and just instinctively knows it's time to spray for rust. As these sensor networks expand, and as this digital nervous system becomes infinitely more perceptive and mathematically precise than human senses ever could be, will we eventually reach a point where that traditional intuition of the farmer is entirely replaced by autonomous software? Are we quietly watching the dawn of a fully automated natural world?
It's a huge question. It really forces us to seriously consider what the role of the human in the loop will actually be as these planetary-scale IoT systems reach full maturity.
It certainly does. Well, that is definitely something to keep in mind the next time you look out at a field or, even just check the weather radar on your phone. Thank you for joining us for this deep dive. Keep questioning the invisible systems around you, and we will see you next time.